So this is a spot where, you know, some art skills kind of feel important, but they don't have to be. You know, let's say we have this function f and this function g, which is like a line, and this, right? So this is our region here. Now there's two different ways I can rotate it. One way is to rotate it around the x-axis, or any other horizontal axis is going to be very similar. And so when you do that, you know, whether or not you actually think of what the shape is going to be, the three-dimensional shape is not actually that important. I don't need the three-dimensional shape here in order to come up with the sort of setup of what I need. What I do need to remember is that this is going to be the center. The axis of rotation is always going to be the center. So any radii or heights are going to be measured sort of from this. So what I like to do is not actually mess with the whole shape. I like to just focus on the disc that gets cut out. Now, I'm choosing a disc in this case because of this function, the way this function f looks. It's really hard for me to think about taking slices this way. It's much easier for me to take slices this way. And so I don't even actually need to draw that kind of fake three-dimensional disc. I just need to recognize that I have this like outer radius and this inner radius. And I'm very sympathetic because it does get messy to visualize what's going on. And there's a lot of things going on, but there's actually not that much that we need to focus on, right? This is a washer. The slices, because it's sliced vertically like this, the slices are dx, right? Little slices of x. And then this value here is a y value, and that y value is equal to whatever the function is, f of x, right? If this function was x squared plus 2, I'd put in x squared plus 2 here. The lower function, or the lower part of that, is g. So that's going to be g of x. And I get to do that because it's just rotating around the x-axis, right? If that's at a different value down here, say y equals a, I get this much larger, I get this huge disk kind of thing if I did that. But I don't need to worry about what it looks like. I just need to figure out what's the outer radius and what's the inner radius. My picture maybe is getting terrible here, right? But so this would then be f of x minus a, right? Because I take this upper value minus the lower value. The a is clearly a negative value, so minus the a would actually be like plus 3 or whatever this might be. Be the same for the g of x. Now, if I rotated it this way around the y-axis, it it's very difficult to think about how I could slice it like this, because I'd be getting all these kind of different kinds of slices. And so it's going to be much easier to keep this one sliced like this, like a little dx again. But when I rotate it, dx, when I rotate that around the y-axis, that's going to create this washer, right, or cylinder. And I don't really focus too much. I mean, when I do these, I'm not thinking about like the shape, like the visual shape of the thing. I'm only using this little picture to help me organize and see what these values are. When you do cylindrical shells, the radius of the shell is always a version of the variable that you're integrating by. So this is always going to be basically x. It could be x plus 2 or 2 minus x or something like that, depending if I'm doing a different axis of rotation. But the radius is just an expression of x when I'm doing dx. The height here is related to the functions. Right. So the height in this case would be the upper function minus the lower function. Right? Distance is always upper minus lower when we have two functions like that. Were either of those or any of that getting at your question?
Yes. Yes. I think I just have to be a little bit more organized, but yeah, I think I was uh putting a little bit too much emphasis on like the drawings. Because I get the math. It's just sometimes I feel like I'm just doing the same pattern without understanding it, sort of. So yeah.
Yeah, and I mean the drawings, they can sometimes be a distraction a little bit, like going back to this cylindrical shell problem. I really just need like this and this. Like those are the only two kind of dimensions that I need, right? This is x, this is f of x minus g of x. And that's all I need to really plug into and use that formula. All the other three-dimensional stuff is not actually necessary. I do need to see how F and G and my axis of rotation, how those interact, because that's going to determine whether I've got like a hole in it or which is the top and which is the bottom function and some of those choices. But after I see that area, yeah, we don't have to focus very much on the three-dimensional aspect of it. And there is a little bit of like kind of just following the procedure work a little bit. You were kind of hinting at, I think, where you're kind of just like going through the pattern each time. That's not crazy with these, because we do have this kind of pattern, right, or structure, but we do need to make good choices so that we pick the kind of the right pattern or structure with them. And that's where I think yeah, probably the most important point for most of us is just seeing and picking the right structure to work with. I don't know. Sometimes people ask questions and I'm like, I know that this is perfect. I know how to answer that one. And this question, I'm not sure I hit the nail on the head, but hopefully you gathered something out of that. Other questions? or other topics that you are maybe concerned about? Yeah, let's take a look at this. Okay, so this is a derivative question, and I think, I don't know if it was capital F or lowercase f, right? It's not so important here, but it's, I think, just a straight derivative question, right? So, and that's part of this too, is that when you see these kind of questions on the final, I mean, we've done all kinds of different things with functions, right? We've rotated them around to find volumes, and we've found their max and mins, and we've found limits and continuity and all kinds of different things. So just looking at the function, you need to make sure you're thinking about what you're trying to do with that function, right? Do not go on autopilot and say, oh, I kind of remember this function and I just do this and this. You got to make sure you really read the question and know what's being asked. So I think this question is just finding the derivative. So this is really, I don't have any of that other stuff going on. I'm just using my derivative rules. And so I want to just be kind of careful that I'm thinking and showing the structure of the problem, right? So this is really like an e to the u. So the derivative of e to the u is e to the u times the derivative, right, of that u. So that's the way the chain rule works, right? And then when I look at the derivative of this, I really want to see that as a product, right, first and foremost. So I'm going to use the product rule here. The derivative of 8t, right, plus 8t times the derivative of sine of 2t. And there's a little extra chain rule there, right? The derivative of sine of 2t is the cosine of 2t. Times 2. It's possible to do a tiny bit of simplification here. You can pull an 8 out of both of these and put it in front, but it's not, there's not much to do, right? Typically chain rule problems don't have a lot of simplification because they're already like multiplied together, right? These pieces are multiplied together mostly. Does that answer the question or show what's needed with that? Okay. Yeah, oh, of course. Thanks for the question. You know, and it's certainly a possible kind of question. You know, part of there's a little bit of review material on, you know, actually taking the derivatives. So some of it is just part of doing the things. You need to know derivatives, but you know, I'll probably throw in 1 or 2 questions that are something like this, where you can really, you know, a more complicated function, but that you can take the derivative of. Let me just, so here's our list. This is posted on D2L. So final exam focuses on 4, 5, and 6, but there's a few questions from 2 and 3. So basically, like from chapter 2, I'm going to make sure that you know the definition of the derivative and can use the limit, right, to find that derivative. So using that definition, right, and remember the limit f of x plus h minus f of x over h. So that does a little bit of limits, and then it makes sure we get at our derivative. And then chapter 3 is just, making sure you can do a derivative. So this question we just did would have been like one of those, right? It uses a couple of these properties to come up with our derivatives. And then the real kind of focus of our final is chapters 4, 5, and 6. Closed interval method, mean value theorem, increasing concave up, both using, so it's like, okay, these look kind of the same. Well, this is using just the derivatives, so algebra, but we also want to be able to do that from the graph, right? We've seen a couple of those questions, I think, both on the take-home work and the homework. L'Hopital's rule, optimization, our general antiderivatives, which now we are probably much better at than we were back when we saw them in chapter 4. And then Newton's method. So again, just make sure you write this little tiny formula that you kind of need. Well, you need. So that's, again, one of those pieces to write down. Chapter 5, 4 and 5 are both real important chapters for us. 4 is like the culmination of our work through derivatives, and then 5 is all this work with antiderivatives. So just really understanding what the definite integral is, what the definition is, right? That's our limit of the sum. Understanding geometry, and understanding how the fundamental theorem allows us to find those definite integrals. And then we did a little bit of extra work with our different antiderivatives, right? Substitution. And then chapter 6, there's kind of these 3 questions, right? Area between 2 curves, washer method, cylindrical shell method. Being able to choose and use and set up each of those methods. Okay. Any other questions on these?
I had a question.
Yeah.
I had a question on the final review on WebAssign.
Yeah. Give me a second here.
Yeah, question 30, sorry.
30, no, that's fine. I'm still working my way there. Okay, question 30. Yes, okay. Okay, so the question actually does give you a little hint or instructions, which I may or may not give you. But you should know that when you're looking for the derivative of this kind of function, that's a fundamental theorem of calculus part 1. This is an accumulation type function, right? And we're looking for its derivative. And so if this were just x, right, instead of tangent of x, we would know what that is. In that case, the fundamental theorem of calculus says it's this, right? That's exactly the statement of fundamental theorem. If you integrate from a to x f of t dt, the derivative of that is f of x, right? Where this function is our f, right? And it's evaluated at x. The rate of change is the height of that function. So that's sort of like the first level, is making sure we see that, right? If it were this problem, its derivative would be that, and that's a good start. The second part is say, okay, well, the derivative, it's not going to x, it's going to tangent of x. So instead of an x, I've replaced that with a function of x, tangent of x. So that means I want to find the derivative by the chain rule. The chain rule says I take the derivative of the original function here, but I evaluate it at my new inner function, which is here. So this is going to become 5 tangent of x plus the square root of tangent of x. Right? So that's this derivative evaluated at tangent. And then I would multiply at the end the derivative of tangent, secant squared. So you're kind of thinking of this as like a known function that you're starting with, is one way to look at it, and then you're just replacing it using the chain rule. You can do this without really thinking about the implications and the theorem of algebra, and I would guess many of you are successful with this in that way, in that you're not really thinking so much about all the intricacies. You're just recognizing the pattern, right? And the pattern is you replace the t's with the tangent, and then you multiply by the derivative of that tangent, right? And that is true, and that is exactly what the fundamental theorem and the chain rules say. So there's nothing wrong with that. I can't tell the difference. And this is one where I think it's hard to grasp sort of the fullness of it. And that's totally 100% normal, right? I still feel sometimes like, it seems a little tenuous even for me, like the why. I mean, I can do them all, but the why it works, you have to get back at the idea of what this definite integral is really saying, right? The area under the curve argument. So does that help?
Yeah, thank you so much.
Oh yeah, okay. Anything else?